In the last lecture, we understood why orbitals have shape. Today, we answer the next unavoidable question. Once orbitals exist, how do electrons decide where to go? The answer is often taught as three rules. Today, we will see that those rules are not arbitrary, they are unavoidable. Electrons seek lowest energy. That's a golden rule here, right? Electrons seek lowest energy. Everything that follows comes from this one statement. Electrons arrange themselves to minimize energy, nothing else. That's very, very, very important statement here. The key statement here, the follows is electrons arrange themselves to minimize energy, nothing else. So let's understand now how the three rules govern uh, the placement of electrons in the orbitals. So the first rule that we are going to talk about today is Aufbau rule. So it simply states that electrons occupy electrons occupy the lowest available energy state first. The lowest available energy state. That's a statement of Aufbau's rule. Now we know that how to find the energy. There are so many rules that determine the energies of orbitals. The famous rule is called as n plus L rule, correct? N is your principal quantum number, L is your azimuthal quantum number. This is how, guys, we can find the energy rule, n plus L rule. Let's say we have to find the energy of 1s, 2s, and 2p orbitals. Then how to decide? Now let's find the n plus L values for each of these orbitals. Here n is 1 and for s orbital L is 0. So 1 plus 0 is 1. Again, this 2 plus 0 answer would be 2. Then guys, it's 2 plus 1, the answer would be 3. So it shows that this is the increasing energy levels 1s, 2s, 2p. All right. There is no chemistry without energy ordering. If the electrons ignored energy, atoms would not exist. So this is how we can basically classify the orbitals as per their energy levels. You can simply find the n plus L values, or there is a very famous electron cutting pattern diagram, which is like this: 1s, this is 2s, 2p, 3s, 3p, 3d. Then we have 4s, 4p, 4d, and 4f. Just cut these orbitals diagonally and you can get your energy level like this. Like this, you can easily cut these orbitals diagonally. And I can show you the arrow points like this. This is 1s, then you have to get 2s, then 2p, 3s, then 3p, 4s, then guys 3d, 4p, and then 4d. This is how we can get these energy levels, right? So you can also verify these energy levels as per n plus L rule. Very, very important rule for energy levels of orbitals. Okay, accordingly you can fill the electrons in these orbitals. We can take some examples after we see all these three rules. Let's move to the second important rule, which is Pauli exclusion principle. The rule number second is Pauli exclusion principle. Now, what does this rule states us? It simply states that maximum two electrons, maximum two electrons per orbital with opposite spins. Very, very important rule. Maximum two electrons per orbital with opposite spin. This is how the Pauli exclusion principle governs to us. You know, why only two electrons in one orbital? Because no two electrons in an atom can have the complete set of quantum properties. All four quantum numbers, no two electrons have the same set of those quantum numbers. Practically, this means same orbital, same energy, same position, spin must be opposite, right? That is why we need to write electrons like one in the top spin, one with the down spin, because no two electrons in the same orbital can have the same set of four quantum numbers. And this thing can be differentiated by having the opposite spins. Very, very important, guys. This Pauli exclusion principle. This is not negotiable in nature. Very, very important again. Let's move to the third important principle, which is Hund's rule. Let's understand the Hund's rule. Now, what does this Hund's rule talks about? Hund's rule gives us an idea about degenerate orbitals. It gives us an idea of degenerate orbitals. Very, very important concept. Degenerate orbitals. What do you mean by degeneracy? Degeneracy means orbitals having same energy. All right. So when orbitals have same energy, electrons avoid pairing unnecessarily. That's very important point here. Let me write it here. When orbitals have the same energy, have the same energy, electrons avoid pairing unnecessarily. That's very important point here. Let me explain you uh, basically with the help of some example. Let's say we have three p orbitals. This is px, this is py, and this is pz, right? Now, it says that, it simply states that because electrons repel each other, separating them lowers repulsion and therefore it lowers energy as well. Let's say, look at that, one electron, two electron, three electron. Just give one electron each to all these orbitals, then start pairing the fourth electron, the fifth electron, and then the sixth electron. Do not pair it immediately. Just basically separates them as long as possible because it lowers repulsion, it lowers energy. This is how the Hund's rule actually basically lands upon. It simply says that maximum separation, minimum repulsion. It simply says that maximum separation, minimum repulsion. Very, very important rule, guys. Hund's rule is not a rule. It is common sense at the atomic scale. So basically, these are the three important rules that we studied so far. One is Aufbau principle, one is Pauli's exclusion principle, third one is the Hund's rule. Basically, all these three rules, they governs the electronic configuration of different elements. Now, let's learn how to apply all these three rules together. Let's start with the hydrogen. You know, hydrogen's atomic number is 1. All right, only one electron we have at our disposal. So we have only one orbital. So guys, answer is 1s1 configuration. Very, very easy. Very easy. Just let us do this step by step, right? Then let's do of helium, guys. Helium, the atomic number is 2. So because every orbital contains maximum 2 electrons. So 1s2. Now it is filled. Now let's go to the hydrogen helium. Let's go to the let's say directly jump to the carbon. Let's go to the carbon. Carbon's atomic number is 6. Now we have 6 electrons. Go one by one. Lowest energy level is 1s, 1s2. Now it is filled. Let's go to the another energy level, guys. After 1s, what comes? Let's go to the Aufbau rule. After 1s, there is a turn of 2s. So 1s2. Now we have 2s2. Now this comes 2p orbital, guys. You know this very, very clearly. 2p orbital, guys. Basically, we have three orbitals. You know that p has three orbitals. Let me draw it again for you. One, 2, and 3. So we have only two electrons left. So it goes like this: 2px1, 2py1. So we can simply write it like this: 1s2, 2s2, 2p2. This is how we can write carbon's electronic configuration. Let's write one more. Let's talk about nitrogen. Atomic number is 7. So how do we write it? 1s2, 2s2, and now how many electrons, guys? 2p3, because there are 3 electrons left. So this times all these 3p orbitals are singly filled. Let's talk about one more very, very important: oxygen. This is where pairing starts now, because we have 8 electrons now. So guys, 1s2, 2s2, and we have 4 electrons left. How many electrons that p orbitals can maximum accommodate? Guys, there are 3 boxes, means 3 twos are 6 electrons it can maximum take. So it still can take 2p4. If I draw the orbital diagram for p orbital, guys, now it clearly shows you the pairing. Now look at that: 1, 2, 3, and 4. Fourth electron starts pairing, guys. Notice something very, very important here: the rule never change, only the atom does, right? Rule always stays the same. The electronic configuration pattern, uh, basically, that changes for each and every element, guys. So electronic configuration tells us how many bonds an atom can form, whether lone pair exists or not, where reactivity will appear. Organic chemistry is impossible without understanding electronic arrangement. Very, very, very important. Correct. So, basically, in the next lecture, we move from the individual atoms to bond formation. We will see how orbitals overlap, electrons are shared, bonds gain direction and strength. So, if these three principles feel logical today, chemistry will stop feeling like memorization and start behaving like a system.